All right, our next speaker is Trey Grainger. And Trey, very interestingly, has been with SDSC since pretty much the beginning. I'm not sure he's ever missed one of our conferences. So Trey is the CTO of a company called Presearch. He's also the founder of Searchkernel, and he's a former chief algorithms officer at Lucidworks. He considered his term search nerd. Welcome, Trey.
I really appreciate it. All right, good morning, everybody. Trey Grainger. I'm the Chief Technology Officer at Presearch, and today I'm going to talk to you about data science for Web3, building a decentralized web search engine. In addition to being CTO at Presearch, I'm also the founder of a search consulting company called Searchkernel that focuses on AI-Powered Search. I'm the former Chief Algorithms Officer at Lucidworks. Before that, here in Atlanta, I was Director of Engineering at Career Builder for search and recommendations. Went to Georgia Tech, got my MBA in Management Technology, graduated from Furman with degrees in Computer Science, Business, and Philosophy, and studied information retrieval and web search at Stanford. I'm also the author of the books AI-Powered Search and Solr in Action. And if you're interested in learning more about search and you're not busy tomorrow, I'm actually giving an AI-Powered Search workshop here at the conference. So I think there's still a few seats open for that last time I checked. If so, definitely consider checking it out. We'll be talking about understanding user intent, signals boosting, semantic knowledge graphs, semantic search, dense vector search, learning to rank, those kinds of things, as much as we can get through in the day. Additionally, if you're not able to come tomorrow, but you're interested in AI-powered search in general, Manning, my publisher, has given a 35% discount code for all data science books for any of the attendees here. So there's a code up there you can use. You can take a picture. And I'll have it at the end of the talk as well, or you can come up and grab me if you're interested in getting anything from Manning's catalog. So Presearch is a decentralized search engine. The title of the talk talks about data science for Web3. And since this is a data science conference and not like a crypto conference, I'm going to assume that a lot of people here have no idea what Web3 is, what it means, and give you guys just a little bit of introduction. So at a very high level, if you break the history of the web into phases, there's sort of the Web 1.0 phase, which is considered the read phase, where people mostly go to consume information. There's the Web 2.0 phase, which is considered the read-write phase. That started kind of early 2000s with the rise of Facebook and different social media companies. This is where users actually both consume and post information, but typically to centralized services and servers. And then Web 3 is the notion of read, write, execute, and own. And in this world, there's not single companies and services that are intermediaries, but users can actually interact with each other on the web through in a more peer-to-peer way. So I'll go through that really quickly. For Web 1.0, if you think back the old AOL days, if you were around then, you've got your Netscape Navigator, America Online, Alta Vista. These are places. This is an era where people publish content, services publish content. Users consume that published content, and while users could communicate with each other with email, chat rooms, things like that, by and large, those were utilities, and users weren't being tracked by big companies in that phase. The Web 2.0 phase is the read-write phase, and so you see, Google up there. You've got things like Google Analytics that tracks you all around the web and builds a profile about you. You've got Twitter, Facebook, Instagram. You're publishing information to them. They're tracking you, and they're trying to monetize you as a product. In this world, services and users publish content. We have the rise of social media. Services track and collect user activity, so things like searches, views, clicks, locations, purchases, etc., and monetize that information. The services with the most content and users typically become the biggest through large network effects. They also become the most profitable, and these services are centralized and actually own the data. So they control access to the data, they can sell the data, they can censor the data. It's their platform, and they can do what they want with it. And then, of course, in terms of like some sort of a warning for this phase, because there are these large centralized repositories of information, anytime those databases have security issues, that can lead to massive hacks and security leaks. Probably every couple of months you get emails from some lawyer telling you you're probably somebody owes you some money because of some data that was lost. And then Web 3.0, the read, write, execute, and own phase is this phase where most data becomes public. There's open storage, peer-to-peer storage, open databases, things like blockchains. Data is owned by end users often and can be controlled by each user if they own data through their cryptographic keys. And in this phase, privacy is paramount, mainly because things are open and peer-to-peer. You have to sort of build privacy in from the beginning. If there is data that's sensitive that's being put out there, it's got to be cryptographically secured using public and private keys. The warning in this phase is instead of having large centralized databases that can be hacked, in this phase, each user's individual keys can be hacked. So if somebody loses their private key, all the information associated with that private key someone else now has access to, and that user can actually lose access to their information and lose ownership because somebody else has taken the key. So that's the sort of caveat for this phase. But it's just that user that was hacked, not every user who was in the giant centralized database. In this world, users directly interact with each other through peer-to-peer mechanisms. They can interact with storage to save information, and they can interact with the execution layers without intermediaries. So instead of Amazon or Facebook or Google running servers that are powering the applications, in this world, the applications themselves can run on decentralized infrastructure, which makes them very censorship resistant and virtually impossible to get down in many cases. Because they're decentralized. And so I've now thrown out another word, decentralized, many times. So what does decentralized mean? So what you see here on the image is it represents 70,000 nodes running on the Presearch network all around the world. And the interesting thing is that Presearch, and these are servers basically, Presearch isn't running any of these. There's tens of thousands of people all around the world running our software, and this is where the software is being run from. And this is all being used to power our search engine. This is what the actual stats look like. You can see there's 73.4 thousand nodes running in our network. There's that 12,000 plus in North America, and about 26,000 in Europe and 10,000 in Asia. This is how the nodes have been distributed around the world. That's a lot of servers, and our community are the ones running these, not our sort of core Presearch engineering team. So lots of interesting caveats with that, but I've mentioned a node, so it's a server running the Presearch software. So we ship the Presearch nodes as Docker containers with our software, and each node in the network can be assigned one or more roles. And so examples of the roles, and I'm not going to go into all of these, but if you think about how a search engine works, the kinds of things it needs to do, one of the roles, for example, is crawling. You have to be able to crawl the web to create an index. There's crawl validation, index routing, model inference, coordinating, index validation, and there's also federation, which can go to external sources and pull information in, storage, decentralized peer-to-peer storage, consensus, which is a blockchain mechanism to be able to have peer-to-peer nodes come to an agreement on something in a trustless way. There are gateway nodes, which I'll talk about in a second, indexing, searching, sort of a message bus mechanism where different nodes can serve that role as well. But again, all this is designed to happen peer-to-peer in a decentralized network. And the graphic on the bottom right there is just, when you start the Docker container, this is the software for the node that's running and connecting to the network. And we've got over 1 billion pulls. I think Docker Hub stops counting after 1 billion, so I think we're one of the larger projects out there in terms of usage. We have this notion of a gateway, and I'm going to get into the data science stuff in just a minute, I promise, but I've got to get you the sort of an understanding of what we're dealing with here and the network we have to try to do data science on. So a gateway for us is a sort of special node. These nodes handle what I would consider sensitive information, sensitive operations. So whenever a user hits a web server and goes to run a search, there's information like the user's IP address and browser information, and if there's any account information, those kinds of things. We don't want that going out to 70,000 random servers that could be malicious all around the world. So the gateway nodes serve the purpose of anonymizing queries, removing IP addresses, things like that are private, logging statistics about searches, retrieving ads, recording stats that can be used to calculate rewards for nodes and searchers. They securely manage keys in some cases, and they run in essentially a trust but verify mode. And so we use something called proof of stake, where if somebody wants to run a gateway node, they have to actually put collateral up, and if anything malicious happens on those gateways, they lose their collateral. So there's a large economic incentive for anybody running a gateway to never do anything malicious, because they're going to get completely hosed financially if they do. The rest of the nodes that aren't gateways operate in a never trust until we verified mode. And so anything that happens on a regular node has to actually be, sort of the work has to be done by another node independently and then verified to make sure that, for example, you don't have a node that's returning bogus search results with some malicious content inside of them, or they're pretending to crawl the web but actually just injecting their business to try to get them to the top of the results and things like that. So there's a lot of validation that has to happen, because in this world, our network is run by servers that we don't trust. And we have to be able to build the software such that trust is not assumed. In fact, we assume that we can't trust any of the nodes unless they can be independently verified by other nodes. So network topology for us, apologies for the being slightly off with the text there, but so we have gateways and we have nodes. Nodes connect to these gateways, or gateway nodes that we just talked about, and additionally we have web servers, and the web servers connect to the gateways as well. Then users can run searches. They run searches to the web servers. The web servers are connected to the gateways that end up going to the nodes to run searches. This is very simplistic here. In reality, you're going to have multiple users all connecting to the same web server to try to run searches, and we've got multiple nodes that will all connect to that gateway. And so the requests can be routed from the user through the gateway to nodes to have the searches executed. And additionally, you can have multiple web servers connected to a single gateway server. And we're still working on some of the peer-to-peer mechanisms, but ultimately the nodes need to be able to talk to each other to do peer-to-peer coordination. So that's one gateway server. And then, of course, we've got more gateway servers. We've got more nodes that connect to other gateway servers, more web servers that connect to those as well, and, of course, users who connect to those web servers to run searches. And so I mentioned we have 70,000 nodes. And so if you think of all of these kind of spread out in a decentralized network, this is what one region might look like. And if we sort of step out a little bit, we've got this happening all across the world in different regions. And so what you see on the left here is a gateway pool, is what we call it. It's essentially a region. It's sort of a cluster of gateways and web servers that provide very fast access to end users. They go to run a search. They hit a local gateway that's in the same region. It goes to they hit a web server in the region. It goes to a gateway that's in the same region and tries to go to nodes that are connected to that gateway that have low latency that can probably return successful results very quickly. The nodes all coordinate with each other. So you see on the right, we also have a similar footprint in Asia. This is in Singapore, where we have another gateway pool set up. And then that all makes sense, except for the network can't be static. And so if you think about how any website works, if you work for a large website, it's going to work this way as well. In the morning, before you wake up, it's prime time day in Europe, right? Over the course of the day in Europe, as it gets later, there's maybe less web activity and more of it shifts to North America. And then as it gets later in North America, more activity shifts over to Asia. And so you can see on the right here, this is sort of a volume graph showing where most of the searches come from at any given time of the day. And on the left, we actually show the breakdown of where searches come from in aggregate from across the world. So what we actually do is on an ongoing basis, the nodes are all coordinating with each other and rebalancing to be able to best handle traffic. So for example, if it's prime time in the US, and the US needs more nodes to stay in balance, then some of the nodes will disconnect from gateways in Europe and connect to gateways in the US, and it's the nodes that have the lowest latency going to the US relative to Europe. And so the network is constantly rebalancing itself to try to make sure that the end user can get the fastest search results as quickly as possible while the network can still stay balanced to be able to best handle traffic. In addition to that rebalancing, we collect lots of stats on each node. So there's what we call a reliability score that's composed of essentially the node's uptime, its latency, and its success rate at returning results within the allotted amount of time. Again, a node could be running on a nice, big, powerful server in a data center, say AWS. A node could be running on a Raspberry Pi in my house, connected to my flaky Wi-Fi and going up and down constantly. I've got a node running on my laptop, which is in the back of the room shut right now, but I'm going to open it back up after this talk, and so that one's constantly connecting and disconnecting. So we have to engineer the network to assume that every node is flaky and untrustworthy, and we leverage them as best as we can when they're available to be able to power search results. And so every node operator, if they have a more reliable node, that node's going to get more searches, and also we have a mechanism to be able to compensate node operators for their cost in terms of running on the network, which I'll talk about in just a minute. But all the node operators are essentially trying as best as possible to have the most reliable nodes possible. And so during the course of the day, this is what these 70,000 nodes, which are the yellow dots here, might look like, and how they're connecting to these gateway pools that have web servers and gateways. And these white lines might kind of move around throughout the course of the day as things are constantly rebalancing. So that's technically what we have, the network we've built, the nodes, how they work, and how things sort of happen in a peer-to-peer way. But let's back up for a second and talk about why we're building Presearch. So this is a graph from Statistica from July 2022 showing the worldwide desktop search market share. And you can see here Google, worldwide is coming in at 83% of all global searches. I'm not sure why Baidu's not on this one. Maybe I grabbed the wrong one, but they should be somewhere up there. But this is a problem. Like if Google is essentially acting, or if search engines in general are acting as the gateways to the world's information, having one company with this much control over the information that you see on a day-to-day basis, what shows up, what doesn't show up, that's a lot of power, and this is probably not ideal. And so let's say we wanted to compete with Google. It's really, really hard, right? Nobody can raise enough money to outcompete Google or Baidu. Nobody's going to raise enough money from VCs to go hire, thousands and thousands of the smartest people in the world. They're taken, and it's just a really hard problem. And so our view is that instead of trying to compete head-to-head that way, that the best strategy to build a competitor is to allow everyone in the world to collaborate, to have a community-first search engine. So that means while everything's not currently open source, much of it is, and eventually everything will be completely open sourced. This means that anybody in the world can contribute ideas, algorithms, code to try to build this thing up. And what we're focused on right now is really securing a viable long-term economic model for the incentive structure. So if somebody's running nodes, they're providing computing resources. They're running those instead of us paying for servers. They should be compensated. Advertisers are getting traffic from end users. They're going to be paying for that traffic, just like the advertising model for search is well known. I don't need to go into how lucrative it is, but being able to sort of take this, and instead of having a company trying to make as much money as possible, if we can take that money coming in from advertising and turn around and use it to fund building out the network and to incentivize all the players in the network, we believe that over time we can actually attract the best talent in the world to be able to want to contribute to a large open source search engine that ultimately we hope could become the next big thing. Another thing we have to do is, because we're building this out in a peer-to-peer way, we have to respect privacy from day one, right? We have a bunch of nodes, they're not trusted. We're not going to be putting IP addresses and queries and things like that out there into the open. That would be ludicrous, and nobody would trust us or use us. But if we can build privacy from day one, not log user searches, just protect everything so that when you use the search engine, it's completely private and you can trust it. And we can do that from day one, then we can build towards the long-term decentralized ownership and operations, which I described earlier, which is at the heart of Web3. So this is sort of the business model. I mentioned the economic incentives. Very simply, you've got advertisers. They want to spend money to advertise to get eyeballs, right? So somebody can advertise, that's revenue coming into the network. That revenue can then be divided. So some of it maybe can go to searchers as rewards for things like referrals, or maybe even some search rewards, which is something we do currently. The node operators are running software, so the node operators who are running the best nodes that are getting the most searches that are performing the best, they're going to get the most reward. Additionally, developers and other contributors to the network who are committing code and features and those kinds of things, they can be compensated as well. Our core development team and marketing team, they can be compensated. And so this general economic model of advertisers give us revenue, the revenue goes out to power the network grows, more users come in, that powers more advertising, et cetera. That's the sort of business and economic model here. The idea, though, is to pump all of that value back into the network to grow it, and have it be collectively owned by the community, as opposed to a centralized company trying to make as much money as possible. So now to search and to the data science side of things. Now that you know what we've built and the sort of interesting and tricky challenge of doing things in a peer-to-peer decentralized way, this is a diagram from my book and something I talk about a lot in terms of understanding user intent and the dimensions of user intent. And in this case, I've essentially got 3 circles. I've got a content understanding circle, a user understanding circle, and a domain understanding circle. And so there's some interesting and tricky challenges here with content understanding. So imagine building out a search index. Usually you would have a bunch of servers right beside each other, all with portions of the index. Often you would divide information based on, you would shard information based upon documents, and you can essentially brute force send every query to every shard and bring results back. That's not feasible with us. We've got 70,000 nodes. Some of them are flaky, some of them are more reliable. But the reality is there's no way we could send every query to thousands and thousands of nodes, because essentially these nodes, some of them are really tiny, and our index has to be essentially micro-sharded. So that there's tricks and challenges there. In terms of user understanding, I already mentioned that we have to protect privacy, and we can't store queries, and we can't store things like user signals and behaviors and click logs, the kinds of things that the big players like Google store. And so we've got a sort of challenge there from the beginning. The knowledge graph we can do, but again, some of this information, like even what are our top queries? Well, there's ways to get that information, but if we can't log the queries, it's hard to figure out what your top queries are without some pretty sophisticated sort of hashing and cryptographic protection of this stuff coming in. So every problem that that I've solved in other organizations where we've had search teams, where we just collect information and keep it secure in a database, we can't do that with Presearch. We have to sort of engineer from the ground up better solutions to protect users and cryptographically protect this information. So centralized versus decentralized search, there's a handful of problems here. There's the user understanding and personalization problem. In centralized search, we can aggregate and process user profiles from centralized data stores. In decentralized search, user info is only accessible by each user on their device using their keys if it's collected at all. So essentially our data science problems become edge problems. We have to push the models and the model building to the edge where the user has the information, because we're not going to take that information and push it out to a public database, a blockchain. Or even IPFS storage, which is a decentralized storage mechanism we leverage. For model building, the standard method is you build models offline from full data sets and then you deploy them. In centralized search, all data is typically available in large trusted data stores at any time for modeling. But in decentralized search, the data is spread across thousands of nodes and is expensive to aggregate and is potentially malicious in some cases. And then for sharding, like I mentioned earlier, you typically in centralized search would shard by document and federate queries out across multiple shards. In decentralized search, though, we're hyper-sharded, and we have to shard the content so that queries target only a small number of shards, since the network and servers are unreliable. And so throughout the week, I've heard multiple talks on vector search. There's the theme, it seems, this year, so I'm not going to go into detail in terms of how this works, but needless to say, for us to be able to build an index that is able to be micro-sharded, and for us to be able to route queries there, we have to follow a very different model from traditional search. So in traditional search, you would have an inverted index. It would be keyword-based. You would search for those keywords, and then you would rank based upon what's called TF-IDF or BM25 ranking. In vector search, which you've seen multiple times this week, we instead take the content and we map the words, the phrases, the sentences into embeddings in these vectors. We leverage these transformer models that can take in input, map it to vectors, and then generate similar output if you were to decode it. In our case, for search, what we end up doing is take every document that is crawled from the web, we index it as vectors. We take queries coming in, we index those as vectors. We take those vectors, and we have to map them into approximate nearest neighborhoods. And so these essentially not only become our way of filtering down search results within a shard, these actually become the key mechanism by which we are able to generate the shards to begin with. So imagine taking all the content, generating neighborhoods, and then making those neighborhoods the actual shards in our architecture. So essentially the model is the network. The network is not just the servers and that run the models. We actually use the models to create the network. Again, we've seen some talks on approximate nearest neighbor stuff, so I'm not going to go into detail into that. This is an HNSW algorithm. I've heard that like 5 times this week as well, so I'll let you guys consult the literature on that. But ultimately, what we want to build at Presearch, once we've solved a bunch of these problems that we need to have good search out of the box, what we want to build is not really a search engine. I've mentioned already that we want the community to be contributing ideas and algorithms. In order for that to work successfully, what we actually need to do is not build a search engine. We need to get a base level, good enough search engine that people want to use. But what we need to build is a framework for other people to build search engines, and a framework that can measure the quality of the contributions to the engine. So let's say I have a data scientist who comes in and says, hey, I think I can improve the search and ranking algorithm. And they contribute some code, it's built, it's added to the network, and then the network says, hey, let's test this. Let's show it to 1% of traffic and see how it performs. Let's measure it, and if it performs better than the other algorithms, let's show it more. And then that person can get a higher reward in terms of payment from the revenue coming in from advertisers because they have substantially improved the network. So what we ultimately need to do is use things like click models. This is a simplified dynamic Bayesian network example, but we essentially need to be able to measure improvements and allow people to contribute and get value based upon the value that they're contributing to the network so that the whole network can grow and people can be rewarded for the value they've contributed. So unique challenges we have, we've got things like, with decentralization, we've got things like when crawling, all nodes are untrusted, so each node must duplicate and validate most of the work to ensure there's no malicious content. We've got challenges tracking top queries without some sophisticated hashing and cryptography. The servers I already mentioned can connect or disconnect at any time, so we actually have no control over what version is being deployed because we're not doing the deployments. The community members are doing them. All we can really control is what's the minimum version to sort of force the nodes to upgrade or be kicked off the network. And eventually all the work will be coordinated through peer-to-peer mechanisms, IPFS and blockchains. So there's some very unique privacy and engineering challenges there. And so in summary, just some takeaways. I hope this has been an interesting problem for you to look at, maybe something you haven't ever thought about before. But in terms of the needs, my view is the world needs a community-owned decentralized search engine. There's a small number of people at a few companies controlling access to the world's information, and that's not good. Having to allow tracking and monetization of your private activity, your use of the web, your mobile location, who you communicate with, that's a privacy trade-off that you really shouldn't have to make to be able to get best-in-class search. Additionally, the core Presearch dev team is ultimately building a framework for building search engines and measuring the improvement of those contributions. So long-term, all contributions we hope will be community-powered and governed, and the network will be owned by the community. And finally, building a web-scale decentralized search engine is hard. You've seen some of those challenges. There's many unique challenges, but it's also very rewarding. So that's my talk. Again, got a AI-Powered Search workshop tomorrow if you want to come. There's the discount code again for the book or anything from Manning if you want to grab that. And I don't know if I've got time for maybe 1 or 2 questions, but
Yeah, we can
that's
take
it.
a quick one if you don't mind.
Okay.
All right, hold on one second. Let me get to you.
Thanks, everybody.
Yeah, thank you, Trey.
Question is, thank you, that was very good. Who run the gateway nodes?
Good question. Good question. So currently, the Presearch team is running the gateway nodes. The whole their what do I call it? Trust but verify mechanism. So we've got a little bit of work to do still before we're confident putting that out for other people to run, and specifically around, I mentioned the collateral requirements for proof of stake. So we've got a little bit of work there to do. We're really focused on the nodes, the regular nodes themselves, and a lot of the operations, the crawling, the indexing, the validating. Some of that stuff isn't fully built out yet, and so we're focused on getting that done first, and then we'll open up the gateways to anybody to run, with collateral.
One more? Yeah. Oh, well, that was easy.
So you have a first mover advantage, but I think you said it's open source. If someone forks your project, what happens to Presearch?
Yeah, great question. So I mentioned that some of it is open source. All of it's not open source yet. The sort of core backend and some of the algorithms and some of the infrastructure code isn't yet open sourced. We're trying to strategically, kind of to your point, we're trying to hit critical mass where there's a lot. I mean, we've got 70,000 people running the software. Some of that is open source, and you can go on our GitHub and you can fork it. You can add contributions. We've got our packages where you can make different things come back in search results. But the sort of open sourcing of it will be strategic, based upon kind of critical milestones in terms of adoption. And yeah, like to your point, we don't want people forking it and just completely like taking away the incentive and market share. But yeah, the end result is it'll all be open sourced, and when the time is right, hopefully we can time it right. Yep.
Excellent questions. Thank you, Trey.
All right. Thank you, guys.